is the final part on light polarization. In this lecture, we will discuss about polarization on polychromatic light and photoelasticity, as well as optical activity that modifies the state of polarization. Here are beautiful slides of what we call polarizing art made by students. All you need are a thin clear sheet of plastic, cutter, or a pair of scissors to cut out the desired shapes from cellophane tape. Then you stick multiple layers of the cutout shapes onto the plastic sheet to make the desired pictures. Placing the prepared slides between two cross polarizers will bring out the brilliant colored patterns. Okay, now we talk about polarization of polychromatic light. If we put a retardation plate between a pair of cross polarizer, and if we rotate the analyzer by 90 degrees, then you will see complementary colors, meaning that the complementary colors are colors whereby when you combine them, you give you back white light. Now, for example, if you take a half-wave plate, that red light, and this red light that comes from a beam of white light will be fully transmitted through the cross polarizer, whereas the shorter visible wavelengths will be blocked or maybe partially transmitted. Now, if this TA, transmission axis of analyzer, is rotated by 90 degrees, then the red will be blocked while the others will be transmitted. We will make a demonstration afterwards. Now, the phase difference introduced by this retardation plate is actually dependent on wavelength as well as the thickness of the retardation plate. For example, if you put a crumpled piece of cellophane tape between cross polarizer, you will see colors like that, because when you crumple it, there will be places where there will be locations of different thicknesses. So that's why you see many colors is thickness dependent. And turning 90 degrees will give you the complementary colors. So it also depends on wavelength, as you can see. So this will be the demonstration. As you let's watch. That's a cellophane tape, linearly polarized from the screen from a laptop. And then when I put a polarizer sunglass in front of it, you can see the colors. As I rotate it by 90 degrees, you can see the complementary colors. Let's look into photoelasticity. Well, it has to do with changes in the optical properties of the material. Basically, you will have induced birefringence when the material is being stressed. And this material that we're talking about usually dielectric media. And from the fringe patterns, especially when the points where the stress is high, then you have very dense fringe patterns. So from here, you can look at the stress distribution of that particular sample. So here, we have a simple setup for doing that. Here, let's say we have unpolarized light and we have a pair of linear polarizer and analyzer. So they're at crossed transmission axis. So no light will emerge over here. But when we add a birefringent material in between this polarizer and analyzer pair, then you will be able to see beautiful colored patterns. For example, if you look at this sample here, why is that so? Well, let's take an example. If we add a half-wave plate with the fast axis vertical, then the linearly polarized light after the polarizer, the plane of polarization, will be inclined in this direction. So now we can resolve this into a vertical, which is a parallel to the fast axis, and a horizontal component, which is parallel to the slow axis. But when this light emerges from the retarder, then the fast axis plane would then have a phase of pi ahead of the slow axis. So when you superimpose the two of them, what you get would then be a linearly polarized light as well. But in this case, the orientation of the plane of polarization would have rotated by 90 degrees in this case for this half-wave plate. And now this would be the plane of polarization. And because of this, then light would be able to pass through the analyzer because this plane of polarization is parallel to the transmission axis of the analyzer. Now, to prove it mathematically, let's use Jones vectors and matrices. Now, the state of polarization after the linear polarizer, we can write it in this form, that's Jones vector, whereby the angle is 45 degrees, and that will give you the state of polarization given by this two-element column matrix, 1, 1 here, so linear polarization at 45 degree angle inclined. And then we operate this by a half-wave plate matrix, where the fast axis is vertical, that this will be represented by this matrix here. So when you multiply that, your output will then be still a Jones vector. So this gives you the state of polarization, whereby the element now will be 1 and -1. And this tells you that the output from the half-wave plate would be a linear polarization inclined at an angle of -45 degrees. Now, since the linear polarization now is parallel to the transmission axis of the analyzer, then it will be fully transmitted by the analyzer. And the final light that emerge from the analyzer would be at a state of linear polarization, whereby the plane of polarization now is inclined at -45 degrees. Now, if the retardation plate is a full wave plate, then the phase difference introduced would be even multiples of pi. And the light that emerge from the retarder is at linear polarization state, whereby its plane of polarization would now be perpendicular to the transmission axis of the analyzer and no light will pass through it. But if the retardation plate were to introduce a phase difference which is not equal to m pi, that means it's not a half-wave plate, neither is it a full-wave plate, then elliptical polarized light will be produced, and some portion of this light will be transmitted by the analyzer. So there would be a phase difference that's introduced by the retardation plate. If the retardation plate has a thickness of d, and it would be wavelength dependent as given by this expression here, where we have a wavelength multiplied by the phase difference, and that's equals to 2 pi d multiplied by the difference in the refractive indices due to birefringence in the material. So usually this difference is small. If we were to neglect this small difference, then this term would actually be quite constant for a given retardation plate of thickness d. So this means that if you just look at this one, if this part is a constant, this will mean that the retardation, which is given by the phase difference introduced, that is delta phi, will be inversely proportional to wavelength. Now, just now in the example where we had a half-wave plate, if this half-wave plate is for red light, then red light would be fully transmitted, and the shorter wavelengths would then only be partially transmitted. But if we were to rotate the transmission axis of this analyzer, so if we rotate it such that TA here now becomes parallel to TA of the polarizer, then the block components earlier would now be transmitted. So red will be blocked, but the shorter wavelength would be transmitted. So in other words, you see the complementary color now. So for example, look at this. This is the image showing the stress on this ruler, right angle ruler here. And this is when the polarizer and analyzer pair are crossed. Over here, they are parallel. Now let's look at the arrow where it's pointing over here. And this part here is white. Here is black, so they are blocked off. Over here, this reddish arrow here is pointing at this part here. So at the same part with the crossed polarization, then you see sort of a turquoise color. Now over here, at this point here, we should see as blue, whereas here you see as yellow. So these are the complementary colors. These are color pairs. When they add up to cancel each other, they will produce either white or black. And these are based on RGB model, which again, as you can see here, the color chart. Now, the complementary color of red will be cyan, magenta will be green, blue will be yellow. As you have seen here, blue, you get yellow. This turquoise color is somewhere between here and here, so you'll get this rose color over here. And this is black, complementary is white. Now, what is optical activity? Well, when a linearly polarized light enters an optically active material, for example, quartz here, it will then emerge still linearly polarized, but would have its plane of polarization rotated from the original orientation. See, this is where it enters, this is how it exits, this plane of polarization here. So the state of polarization is modified. Now, if you were to view it head on, the beam coming towards you, then if the rotation is clockwise, then it's called dextro because it's right-handedness, and it is anti-clockwise, then it will be levorotatory, that's left-handedness. And examples of optically active materials include quartz and sugar crystals for solids, turpentine sugar solution for liquids. Then how does this optical activity arise? Now, if you look at the crystal structure of quartz, for example, both the dextro and the levorotatory behavior actually correspond to the crystallographic structure. Here, quartz molecule is made out of silicon dioxide here. They are identical, but they have two mirror image arrangement of each other, which we call them enantiomorphs. And because of this, it brings out the anisotropic property when it reacts, when it interacts with E field of light. So this material, which is optically active, would then modify the state of polarization, and it produces a rotator mechanism. And this is different from the retarder or the retardation plate, the quarter wave plate, half wave plate that we were discussing before this. So optical activity actually involves birefringence. Yes, we have two refractive indices, but it is due to circular birefringence. So you have NL and NR, where R stands for right, L stands for left-handed circular polarization. Whereas the retardation plates involves also birefringence, but ordinary birefringence, which was assigned whether it's parallel or perpendicular to the optic axis of the material. Now, why is NL and NR different? Well, this material actually has molecules or crystalline structures that have shape which looks like a spiral. So it has certain chirality. It can be either left-handed or right-handed screw forms. And linearly polarized light, when they pass through this collection of these molecules, it will create forced vibration of the electrons. And that would respond by moving along a spiral as well as around the spiral. So the effect of the left circularly polarized light on a left left-handed spiral would then be different from its effect on a right-handed spiral. That's why it will give rise to different speeds through the material. Now, how do we demonstrate or measure optical activity? Basically, how do we measure the rotated angle? Well, if we have a set of polarizer and analyzer, initially set them at crossed transmission axis, so you get total extinction. And then you insert the active cell in between them, and you'll find that you'll see light emerging. So the extinction disappears. So you'll need to then rotate the analyzer by an angle beta to get back total extinction. So the angle that you rotate will then be the rotation angle due to optical activity. So this, and then now here we define some terms called specific rotation. Here is actually for solids is defined as the amount of rotation in degree produced by 1 mm thickness of this material. If it's in liquid, then it will be the amount of rotation due to 10 cm. 10 cm. 10 cm is about this wide thickness, and the liquid must have a concentration of 1 gram of active solute per cm cube of solution. So having defined that, so for optical activity in solid, then the net angle of rotation would then just be rho L, where rho is a specific rotation, L is the thickness that the path passes through in the solid. For optical activity in liquid, the net rotation beta will be due to if the thickness of that solution is L decimeter, and the solution has d grams of active solutes per cm cube, then beta would just be the taking the product of rho L and D. And we also see rotatory dispersion due to optical activity. So if you pass a white light through an optically active medium, each component wavelength will be rotated through a slightly at different degrees. So because of that, the colors can be separated. For example, here we have specific rotation for quartz, and it's dependent on the wavelength. For the shorter wavelength, the specific rotation is larger. For longer wavelength, then it is smaller. So you can see here, you can guess right, red will be rotated less, and comes yellow, green, blue, and violet, because violet will be of the shortest wavelength. Next, we would like to relate the specific rotation to some physical parameters. Now, in an inactive medium, you'll find that speed of the left-handed circular polarized light, it will be equal to the speed of the right-handed circular polarized light. So it follows that NL would then be equal to NR, and also KL, which is a propagation constant, will also be equal to KR. And the magnitude for this propagation constant is given by omega over V, where omega is the angular frequency and V is the speed in the medium. Now, for a linearly polarized light in the x direction, so you have this vector in the x direction. Now, but this light, this ray is actually coming towards you, but it's a linearly polarized light in this direction. Now, it is made up of equal amount of EL and ER. So at t equals to 0, the EL and ER are both aligned along x, so the resultant would be up to here. Now, as they move up to time t1, the angle rotated by EL is this much, the angle rotated by ER is this much. They are equal amount. So EL and ER, we have the resultant, which will be the diagonal of this parallelogram, will still lie on the x-axis. Then as they rotate more at t2, again the resultant lie along the x-axis. And then as they become vertical, then this will be here. And then as they both pass the 90 degrees, EL has rotated more than 90 degrees, ER2 has rotated clockwise more than 90 degrees. At T3, the resultant again is along the x-axis, so you still get a linearly polarized light along the x-axis when you superpose EL and ER. Now, this is an animation of the superposition of left and right circularly polarized light in an inactive medium. Now, the green is representing the left circular polarized light, while the red represents the right circular polarized light, and blue is the resultant. So we look at this plane here. As they move, as they reach this plane, and when they add up together, you find that the blue is just moving up and down. So this is a vertically linearly polarized light. Okay. Next, we will consider the active medium. In this case, the speed of the left circularly polarized light will not be the same as the right circularly polarized light. And then it follows also that NL will not be the same as NR and KL not the same as KR. So in other words, the phases of the left and the right components are not equal. And here we write the complex amplitude for the left circular polarized light. And here is the amplitude of the component, and here is the time function. And here is this one relates to the right-handed circular polarized light. And here you'll find that KL can be written as omega over C multiplied by NL, KR as omega over C multiplied by NR. And the real fields of this will just be taking the real part of this expression. So now the complex vector amplitude, we will represent using Jones vector for the left circular polarized light and the right circular polarized light. You have one I and one negative I, and the prefactor here will give amplitude. So if the E field is E0, so they have been divided into equal amounts. So we write this as half E0 and this is half E0. And the phases of the left and right component then are given by, for theta L, that will be given by KL Z minus omega T, and theta R will be written as KRZ minus omega T. So now, upon entry into the medium at Z equals to 0, at T equals to 0, then you find that we have a theta L equals to theta R, that will be 0 because Z0, T0, this will be 0. But as it moves into the medium up to a distance Z, then if theta L is larger than theta R, in this case, it will be a left-handed rotation. And here, if it is theta L smaller than theta R, then it will be a right-handed rotation of the linearly polarized light. For the left-handed rotation, this is how we consider. Now, at time t later, let's say they start from, at t equals to 0, they start both EL and ER are lying at X. As they enter into the material at time t later at the position Z, then theta L would have rotated anti-clockwise by this amount, and theta R rotated clockwise by this amount. And the resultant would be the diagonal of this parallelogram. And you'll find that it has a positive beta. The net rotation is a positive angle beta. So the relation between these angles are theta L minus beta will give you theta R plus beta. That's equation 4 here. And for this left-handed rotation, which is level rotatory, you get positive beta. And in this case, though, theta L is larger than theta R, but the speed of the left-handed circular polarized light would be slower than that of VR. And from this expression, you'll find that KL will be larger than KR. Why? Because K is related to omega over V, so it's reciprocal. And therefore, theta L would then be larger than theta R. And it also follows that from here, it also follows that NL would be larger than NR. For the right rotation, then you have theta L smaller than theta R at time t. or after having traveled z distance into the medium. So this is dextrorotatory. We have a resultant rotation of negative beta. In this case, VL will be larger than VR, but KL will be smaller than KR, and theta L will be smaller than theta R. And here it also follows that NL would be smaller than NR. So the two components EL and ER have the same time dependence, right? And they are actually in phase. That's why when they superpose, you get a linearly polarized light. So anywhere along the direction of propagation at any position of Z, then the resultant is linearly polarized state. The only difference is that the orientation of the plane of polarization would be a function, would change as you travel into the material. So it's a function of Z. So as the two components, they are of equal amplitude. So the resultant E oscillation is actually the diagonal of an equal-sided parallelogram, so that the angle rotated, from the equation 4 that we saw just now over here, this will give you beta, bring over here 2 beta equals to theta L minus theta R. So beta is equal to half theta L minus theta R. And substituting equation 3, which was the phases, into equation 5, then we expand this EL, substitute this one inside, you have KL Z minus omega T minus this. Now this term and this term cancels, that leaves you with half KL minus KR multiplied by Z. And if you use the relation KL relating to K0, which relates to the wavelength in air or in vacuum, then KL will be K0 NL, KR is K0 NR. So then equation 6 then becomes, substituting for KR, we write as here, we write as 2 pi NL over lambda 0. 2 pi ml over lambda 0. Then we have NL minus NR. Now 2 pi, and these 2 cancels, leaving a pi there. Z is still there, and we have a lambda 0 at the denominator. So this will then give us the angle of rotated angle for a circular birefringent material when the light, linearly polarized light has entered at a distance Z, and the linearly polarized light has a wavelength of lambda 0. So linearly polarized light of wavelength lambda 0 then undergo rotation beta after traveling through the optically active medium of distance Z. Here is an animation of the superposition of left and right circular polarized in an active medium now. Now upon entry, okay, it is vertically polarized, linearly polarized, and then it's split into left and right. And as it travels through the medium, then you find that the plane of the linearly polarized light will start to rotate. And over here, upon exit, it will have rotated by this much. So this is, when you view it coming towards you, it is rotated anti-clockwise. Because here the rate slows down. Here is an example, a sample problem. You're supposed to find the rotation produced by a 1 mm thick quartz plate at this particular wavelength 396.8 nanometer, and thereon find out what would be its specific rotation. As you know, for this optical activity is actually contributed by a circular birefringence. So the values that we're going to use will be NR and NL. And from the equation that we had derived earlier, the rotated angle is actually equals to pi Z, which is the distance it traveled in the quartz plate or the optically active material, divided by lambda 0, which will be the wavelength that we are considering, multiplied by the difference between NL and NR, which happens to be 0.000011. So substitute that 1 cm here is 10 to the minus 2 meters. Then this will give us 499 degrees. All right, so we got the answer for the first part. For the second part, it asks what specific rotation. Remember that the definition for specific rotation for solid is defined by the angle rotated in 1 mm thick of the material. So therefore, the specific rotation would then be this value divided by the thickness of this quartz. So 1 cm equals to 10 mm. So divide by 10, you get 49.9 degree. So that's your answer. Very simple. Okay, now the last slide tells us what you should have learned or what you should be able to do after going through lecture 22. You should be able to explain what optical activity is and how optical activity arises in the material. Well, it's an inherent property of the material, right? Now, and you should be able to calculate the rotation angle that occur because of optical activity. And you should be able to explain how circular birefringence produces linearly polarized light in the optically active material. Okay, so that's the last of the series of lecture that we're doing for optics course for this semester. I hope you have enjoyed it, and all the best to you in your coming exam. Thank you and bye.